So now welcome back to today's session. Again, in the last class, we have seen the representation of a transmission line using ABCD parameters, the short transmission line using ABCD parameters, and also some examples how to calculate regulation and efficiency of the transmission line. Today, again, one more example based on the same short transmission line. Just note down this example. Determine the voltage at the generating station and efficiency of transmission line for the following single phase system. So here the generating station is represented again one step up transformer, transmission line, again step down transformer, and the load is 250 kVA, 2 kilovolts, 0.8 power factor load. So is the entire power system is represented with a single line diagram. So in this fashion, so generator, transformer. So transformer ratio is given 2 kVA to 11 kV. So generation on this sending end is 2 kVA. So whereas so transmitting voltage is 11 kV again. So here it is. So we have to understood. So this 2 kVA by 11 kV is step up transformer here. Again this is the same transformer, step down transformer 11 kV to 2 kV. So load side is again 2 kV transformer. So this is 2 kV by 11 by 2 kV. So here the resistance on LV side is 0.04 ohms. So transformer, the resistance on low voltage winding, that is 0.4 ohms, whereas high voltage side is 1.3 ohms reactance. The reactance on high voltage at resistance is 1.3. The reactance on LV side, that is 0.125 ohms, whereas on HV side is 4.2 ohms. So this is the problem given. So determine the voltage at the generating station. Once we know the voltage at the sending end, we can easily find out regulation and also the efficiency of the system. The first step, we have to find out the voltage at the sending end. Okay. Now coming to solution. So first step, we have to calculate the impedances with the reference to base value. So we have to assume some base value, whether it may be generally the load value is taken as a reference in most of the cases. Here, so if we take, so with the reference to the transmission line equivalent impedance with reference to LV side. So low voltage side means again 2 kV. So same thing here, it is also 2 kV. So this becomes the base values. Okay. Now the first step, we have to, this transmission line is at 11 kV. So that means we have to maintain, once we convert all these quantities into per unit, so that our calculations will be very much simple. Just like one examination, so if we conduct for 50 marks and other examination if we conduct for 100 marks, we cannot equalize those 2 marks without multiplying with some multiplication factor. So like that, with reference to, so one is if we got 25 out of 50, similarly 50 out of 100. So 50 out of 100 is 50% max. Similarly 25 out of 50 is also 50%. If we speak in terms of percentage or per unit values, it will be good. Okay, 50% marks you have obtained. Otherwise, so one is 25, other one is 50. So we don't know the base value, and we cannot speak about the performance of that person. Okay, so like that. First, this transmission line is operating at 11 kV, and this one is this portion is at 2 kV, and again similarly load is at 2 kV. So the first step we have to convert these values either to low voltage or these values to high voltage side. Okay, low voltage side resistance and low voltage side reactance values we can speak in terms of high voltage terms, or we can also convert this in terms of low voltage values. Okay, taking here we have considered taken the impedance value. So here the reference is to low voltage side, referred to low voltage. Now the first step we have to convert this high voltage side values. So resistance on high voltage side, similarly the reactance on high voltage side, we have to speak in terms of low voltage side values. Okay. Now the transmission line equivalent impedance with referred to, first we have converted this values. Transmission line impedance is 10 plus j ohms, 10 ohms resistance, and reactance value is j30. Now we have to convert with reference to, we have not converting, we have speaking the values with reference to low voltage. So, okay, now to convert this resistance, just we have to multiply with 2 by 11 whole square. So how you got this? So this is transformation ratio. The power on both sides, that is equal for a transformer. So using that we can find out. So simply V square by R, or V square by Z if we take. So impedance value we can consider V square by Z. So on right side V1 Z1. So V2 square by Z2 square. So that is on other side. Okay. So this is just if I want to find out Z2 value. So sorry, Z2, it is Z2 value. Z2 is going to be Z2 is equal to Z1 into V2 by V1 whole square. So using this relation, we can convert this high voltage values can be converted into low voltage values, or with reference to low voltage we can speak, otherwise with reference to high voltage. So if we convert this with reference to high voltage values are these values. If these two values belongs to low voltage, we can convert just by multiplying with 11 by 2 whole square. So we can convert these values with reference to high voltage. Okay, is it clear? Just by multiplying multiplying with 2 by 11 whole square. What is this 2 by 11 transformation ratio? So this I think you have learned in machines. That can also be in. So you will come across in machines the same thing. So here the transmission resistance on with reference to high voltage side, that is 10. Now I am speaking the same in terms of with reference to low voltage. So low voltage means 2 by 11 whole square. If we multiply with 2 by 11 whole square, how you got this? Simply by equalizing the powers on both sides. So you will get a relation that is 10 into 2 by 11 whole square. So that gives the resistance.
మళ్ళీ కరెక్ట్ 10 కాదు ఆన్
Okay.
చేస్తే చాలు మళ్ళీ మధ్యాహ్నానికి 1 గంటకి.
Okay. Next, similarly for reactance. For reactance 30 into 2 by 11 whole square, the relation is same. Now this impedance, this is transmission line impedance. So previously this is also a transmission line impedance with reference to high voltage side, whereas this is same values, same transmission line values with reference to low voltage. Okay. Next. Now that coming to transformer winding. So transformer transformation ratio is given 2 kVA by 11 kVA, and also the resistance on LV side is 0.404 ohms. This is not going to change. That is constant. That is values remains the same because this value refers to low voltage. Okay. Again, we have to convert this resistance value which is on high voltage side, that we have to convert with reference to low voltage side. So again the same 1.3 into 2 by 11 whole square. So initially we have converted the values for a transmission system. Now I am converting the values of this transformer onto with reference to low voltage. So here the low voltage resistance is same, whereas high voltage resistance value with reference to low voltage value, that is 1.3 into 2 by 11 whole square. Okay, is it clear? Similarly, reactance value on low voltage side is 0.125. That is same. Okay. Now the reactance on HV side, so if we convert with reference to low voltage side, again we have to multiply with 2 by 11 whole square. Okay. Now everything is with reference to low voltage side. The transformer impedance is converted with reference to low voltage side. So first transformer, second, both transformers are of same rating. So if they are of different rating, again we have to use for transformer 2. The same thing for transformer 2. Okay. So in this case, both transformers are of same rating and same values. So no need to do again. So for transformer 1, you will get the same values. We can use the same values for transformer 2 with reference to low voltage side. Okay. Is it clear? చెప్పండి, చెప్తేనే నెక్స్ట్ స్టెప్ వెళ్ళగలను. Is it clear? Hello?
Yes, sir.
Sir.
Okay. Now, if we draw the equivalent circuit for the same system, so for the same system, if we draw the equivalent, this is the equivalent circuit. So this is transformer 1, whose values transmission line, and again transformer 2. This is transmission line. Okay, here it is load, this is generator. Okay, the equivalent circuit for the total system whose load value is 250 kVA and 2 kilowatt and 0.8 power factor load. So these are the load values. Okay, transformer 2 representation, transmission line representation, transformer 1 representation with reference to low voltage side. Everything is converted into with reference to low voltage side. Here the load is also having the same value, that's why no need to convert. If the load value is something different, again we have to, if there is any impedance, that we have to refer to particular base value. So most of the cases we consider the load values as reference values. Okay. Now the next step, calculating the current. So in this case, the load values are known. So here depends upon the load. If the load is open circuited, current passing through this is 0. So if the load is 250 kilovolt amperes kVA, so 250 into kilovolt amperes divided by kV, directly you will get ampere rating, current passing through this transmission system. So that is 125 amperes. kVA by volts, it comes around 125 amperes. Directly we can find out the losses. Line losses is equal to I square R. See here, I square is equal to, I square means already 125 whole square multiplied with resistance. Resistance of the entire system. So here 0.08 plus 0.33 plus 0.08. So total it comes around 0.496, 7.7 kilowatts. So up to this, in this line losses means it includes transmission line plus 2 transformers. The total losses, so total resistance we have to consider I square into R. So that's why we have to find out this total losses. So we have converted everything into on with reference to low voltage side. Okay, it currents around 7.7 kilowatts. Once we know the losses, we can find out efficiency is equal to output by output plus losses. That is equal to, so because it is a single phase system, so already that is mentioned in the problem for a single phase system. So that's why I have not used 3. So 3 I square R. Okay. So output by output plus losses. Output in kilowatts. Kilowatts means power factor. 250 multiplied with 0.8. So power factor is also given. Output power. So because the load power factor is 0.8. So if we multiply with 0.8, so this is our kVA. kVA into power factor, you will get okay. The efficiency of the single phase transmission line comes around 96.3%. Now coming to regulation. So regulation, so we have formula Vs is equal to Vr into cos phi plus Ir plus J into Vr sin phi R plus Ix. This is from the previous vector diagram, what we have drawn taking IR as reference. So y-axis values, so if we resolve the total component on x-axis, that becomes Vr cos phi R plus IR. If we resolve on y-axis, that is Vr sin phi R plus Ix. Okay. Now Vs is equal to the total. So Vr, that is given, receiving end voltage 2 kVA, power factor 0.8, current already we have calculated 125 into resistance value 0.496, the entire resistance, okay, of the entire system, plus J into Vr is 2000, sin phi R becomes 0.8. If cos phi is equal to 0.8, sin phi becomes 0.6 plus I is equal to 125 again into total reactance. Here reactance of the transmission line and also the transformers, 2 transformers, it comes around 1.536. So total Vs is equal to sending end voltage is equal to 2168 volts. When the voltage is sending end voltage is 2.168 volts, the receiving end voltage becomes 2 kV. Okay, some drop, the drop may be in transformers and also in the transmission. Is it clear? Now we can, okay, so solve some more examples, and if you have any doubts, you can come to me, or in the next class we can able to discuss those doubts. Now, the performance of the medium lines. So medium lines means in the beginning we have uh, based on the length of the line. So length means, again we are speaking in terms of electrical terminology. So if the frequency multiplied with length, length into frequency, it must be in between 4000 to 8000 uh, Hedge meters. So that is classified as a medium transmission lines. In short transmission lines, the effect of capacitance is neglected because the capacitance value always depends upon the length of the line and also the voltage. So here the voltage in case of short transmission lines, which is less than 20 kV, so we can neglect the effect of capacitance. The capacitance value is very negligibly small, and charging currents are also very small. So even though if we consider or if we neglect, we get the same values. As the length of the line increases, so that is in between 80 to 160, or in some textbooks that is given up to 200 kilometers. No need to worry about that. So normally, so 80 kilometers to 160 kilometers, and the voltage range is greater than 20 kV, and also if it is less than 100 kV, so that transmission line is treated as a medium transmission. So in this case, if we observe the capacitance value, it is small, even though we cannot neglect that capacitance. A little bit more, but we cannot neglect. If we neglect the capacitance values in medium transmission line, so if we compare the practical values and the theoretical values, it may not be coincident. So it may get error in those cases. Though we have to consider the capacitance effect of capacitance. Okay, the capacitance of the line is uniformly distributed over its entire length. However, to make the calculations simpler, the capacitance of the system is assumed to be divided in lumped or concentrated form of capacitance across the transmission lines at one or more points. So that means, so here the effect of capacitance we have to consider. So that can be considered as lumped parameters. Even though if we use distributed parameters or lumped parameters, you will get almost same value. So to make the calculations simpler, we can consider the entire capacitance, the distributed capacitance, into a lumped form, and that can be connected at the center or at the ends of the transmission line. So we have to consider the capacitance. That capacitance can be considered as total capacitance at the center, or that can be considered into two halves which are connected at the two ends of the transmission. So that is the most commonly used representation of medium transmission lines are, first is end condenser method, Second one is nominal T, and third one is nominal pi methods. So here, if the total capacitance is considered at the load, total lumped capacitance is considered at the load end, so that is considered as end condenser method. Okay, is it clear? The term itself shows the end condenser method if the total capacitance is assumed at the end. So that means for a transmission system, so resistance, inductance, now the capacitance. Initially, so this is end condenser method. So here this is receiving end where the load is connected. This is sending end where the supply is connected. So if we consider the entire capacitance at the load end, that becomes end condenser method. If the same thing, if we consider the same transmission system, transmission line, so here the impedance value, the series values, so series resistance and inductance, if we made to two equal halves, and the entire capacitance is connected at the center of the transmission line. Okay, if the total capacitance, if we assume that is at the center of the transmission line, that becomes nominal T model. Okay, so that is one more representation of a transmission. The other representation of the transmission line, that is same, the resistance and reactance value series elements is considered as lumped parameters, and this capacitance is made into two equal halves which are connected at the ends of the transmission line. Okay, y by 2, y by 2. The shunt parameters, so that is total admittance or capacitance, is made into two equal halves. One half is connected at the sending end and other one half is connected at the receiving end. That type of representation is nothing but nominal pi model. So nominal pi, nominal T, and end condenser method. So most of the cases we use only these two. No need to consider is end condenser method. So once we know these two, we can also solve this. So that's why I have just given that model. Okay. Okay. So if the transmission line is in between 80 to 160 kilometers length and 200 kV to 100 kV voltage, operating voltage, then that transmission line is considered as a medium transmission line. For a medium transmission line, we have to consider the effect of capacitance. For medium transmission line, we can use lumped parameters. So this entire capacitance can be considered at the center of the transmission line or at the two ends of the transmission. Okay, nominal pi, nominal T. Next, the two most commonly used configurations are known as nominal T and nominal pi respectively. So it is to be noted that the two representations are approximate to the exact representation of the actual line. So once we, even though if we consider the two models, so we'll get almost the same values which are equal to practical values. So that's why these two are very important models in case of medium transmission line. So here in transmission line nominal T, the shunt capacitance is assumed to be considered at the middle of the line. That is one nominal T. In case of nominal pi, half of the total capacitance is concentrated at the each end of the line. Also, the two representations are not equivalent, as can be seen by using a star to delta transformation. These two representations cannot be seen as same, but we can convert into star into delta or delta. Using star to delta transformation, we can convert those representations. Okay. However, they are good enough for practical purposes and do not involve much errors. So if we compare the practical values and theoretical values, the error is very small. Now coming to nominal T model. Okay, in nominal T model means the entire capacitance is assumed at the midpoint of the transmission. The entire capacitance, the lumped capacitance is assumed at the midpoint of the transmission line. Okay, half of the line resistance and reactance are lumped on the either sides of the either sides as shown in figure. In this arrangement, full charging current flows uh, over half the line. Okay, so if we observe the figure, so this is the nominal T representation of a medium transmission line. Here the resistance and reactance values are made into two halves. Similarly, the entire shunt capacitance is connected here. So Y is equal to j omega c. Z is equal to 1 by j omega c. Okay. So minus 1 by j omega c. So that can be treated as admittance represented as admittance. Here this is entire thing is Z by 2. Here this entire thing is Z by 2. So voltage here at this point we consider that is VC. This one is VR is receiving end voltage, VS is sending end voltage, IS is sending end current, VR is IR is sending end receiving end current. Okay, so here only the half of the charging current is flows through the transmission line. So half part is full current is flowing. So again, so a part of the current is flowing through this. Say remaining part flows through this transmission line. So if we consider in this model, okay. So just this is for consideration. So now coming to phasor diagram. So kindly we have to a little bit more concentrating. If we keep more concentration on this uh, phasor diagram, so we can easily understood and we can easily solve the regulation and efficiency for this medium transmission. See here, just considering IR as reference, we can consider either voltage at the receiving end or current at the receiving end as reference values. Voltage kuda తీసుకోవచ్చు reference కింద ఈజీగా ఉంటుందని current reference తీసుకున్నాం. Okay, so current is considered as reference. If we assume the load is lagging load, current always lags behind voltage by an angle something theta or phi r. Okay, so if we consider the load is a lagging load, so current always lag behind voltage by an angle theta. So if we consider IR as reference, so IR at an angle 0, so voltage leads current by an angle theta. Okay, so voltage mundunthundi. Now the same what we have done in short transmission line up to this part. So initially the current passing through resistance, that is IR, voltage drop across R by 2. So voltage drop across this. So voltage drop across this. Okay, so voltage drop across this is in phase with current passing through this. So that's why the voltage across resistance is in phase with current. Okay, this is voltage across resistance. Okay, that is in phase with current. Again, voltage across reactance, that is always makes a 90 degrees angle with a reference with current passing through this. In case of pure inductor, current lag behind voltage by an angle 90 degrees. Otherwise, if we take current as reference, voltage leads current by an angle 90 degrees. So that's why here the angle, if with reference to this, okay, current, this is at an angle of 90 degrees. This is voltage. Voltage across inductance. Okay, this inductance, voltage across inductance, that makes a 90 degrees with resistance. Okay, is it clear? Now, so voltage drop across this becomes the voltage across impedance. This to half impedance, okay, Z by 2. So, which is equal to voltage across this impedance plus receiving end voltage becomes VC. So, VC is equal to, so sum of VR plus V Z by 2. So Z by 2 means here its value is so this is Z by 2. Here it is also Z by 2. Voltage across Z by 2, voltage across Z by 2. This is up to from here to here it is VZ by 2. So addition of these two phasors, resultant phasor is going to be. Is it clear? అర్థమైందమ్మా? చెప్పండి, రెస్పాన్స్ ఇవ్వండి. హలో, అర్థమవుతోందా?
Yes, sir.
ఓకే. సో మీకు అర్థమవుతుందంటే నేను చెప్పగలను, లేదంటే సింపుల్గా నేను ఇంత ఎలాబరేట్గా చెప్పక్కర్లేదు, డ్రా చేసుకోండి అని చెప్పి వెళ్ళిపోవచ్చు. ఓకే, నౌ coming to, once we have evaluated this VC, so current passing through this capacitance. So we have considered the total capacitance is connected at the center of the transmission line. That's why if we consider the total capacitance at this point, so we know that voltage across the capacitance is VC. That value we have obtained. So current passing through this capacitance, that always leads voltage across this by an angle 90 degrees. Okay, so voltage at an angle 90 degrees. So here the voltage across capacitance, voltage, this is current passing through capacitance. So current passing through capacitance and voltage across capacitance both are at an angle of, it is differed by an angle of 90 degrees. So current leads voltage by an angle 90 degrees in case of capacitance. That's why I have considered this capacitance, current passing through capacitance is like this. The same value if we add here, okay, so you will get the net. So same transmitting this phasor here, so you will get IS. IS is sending end current. Sending end current is equal to receiving end current plus IC. Current passing through capacitance. Current passing through capacitance, receiving end current, you will get sending end current. Once we get sending end current, the next step we have to find out voltage across this impedance. Okay, so this is the voltage across R by 2. So current passing through this R by 2 value is IS. So voltage across this is in phase with IS. So that's why I have represented IS and this are in same phase. Voltage drop across R by 2 and IS are in same phase. Okay, next. Again, this is voltage drop across this reactance, that is again making 90 degrees with current passing through the inductor. So current passing through inductor, and if we observe the voltage across inductance, it is perpendicular to this current. So now this gives the total entire voltage drop across. This part gives the voltage drop across one more impedance, half of the impedance. Here V by 2. So this is also V by 2. This is V by 2 impedance. Here it is V by 2 impedance. Now you will get Vs. Vs is equal to voltage drop across this plus Vc. Vc plus voltage across this impedance gives Vs. Is it clear?
Yes, sir.
Okay. Okay. So this is the phasor diagram for a nominal T model. So this is the uh, phasor diagram given in your textbook. A small change here. So it is a little bit if we make like this so that it will be very clear. Otherwise, we can use the same. Okay. The phasor diagram for a nominal T model. Note చేసుకోండి అందరూ కూడా. ఇది ఓన్ గా గీయడం వస్తే చాలు. మన ఫేజర్ డయాగ్రామ్స్ అన్నీ వచ్చేసాయి. మన ఏ మోడల్ కైనా గీయొచ్చు. ఫేజర్ డయాగ్రామ్ వచ్చేసింది అంటే మనకి రెగ్యులేషన్ ఎఫిషియన్సీ క్యాలిక్యులేట్ చేయడం వచ్చినట్టే. కంప్లీట్ అయిపోతే చెప్పండి. నెక్స్ట్కి వెళ్ళిపోదాం. డ్రా చేసుకున్నారా? హలో,
Yes, sir.
డ్రా చేసుకున్నారా?
Yes, sir.
మరి ఎవరైనా అడ్మిట్ అవ్వకుండా ఉన్నారా ఇంటి బయట? ఎవరు లేరుగా. సరే. So next, so for calculation of regulation, the objective first is to calculate Vs. Okay, once we know the sending end voltage, so regulation formula is no load voltage to full load voltage by full load voltage. Here the no load voltage under, so no load voltage minus full load voltage by full load voltage. So again into 100, keeping frequency and supply voltage as constants. That is the definition for regulation. So here, keeping the sending end voltage as constant, the change in no load voltage to full load voltage at receiving end. Okay, so that becomes a regulation. The first step we have to find out the sending end voltage. So simply, so for that from the phasor diagram, Vc is equal to, so this is V receiving end voltage plus drop across impedance. Okay. So if we observe this, so Vc, V receiving end, V sending end is equal to drop across this impedance, half of the impedance, plus Vc. Vc is voltage drop across this. So algebraic sum of voltages in a closed loop equal to 0. So here Vc is voltage across these 2 points, plus V Z by 2 is voltage across this, which gives voltage across sending end. Okay. So same thing what I have written here VC is equal to, this is voltage across, sorry, VC is equal to, VC means this is VC, VC is equal to V receiving end voltage plus Vz by 2. Okay, so both are same. So here VC is voltage across these 2 points, which is equal to voltage at the receiving end plus voltage drop across this half impedance becomes VC. Similarly, Vs is equal to voltage drop across this impedance plus Vc. Okay, we can write both equations from this diagram. So same thing, Vc is equal to, this is Vr, receiving end voltage, this is load power factor, plus IR into Z by 2 plus J into X by 2. Now, the charging current or capacitor current IC is equal to J omega C into Vc. So this we know that current is equal to V by reactance of the capacitance. It comes around J omega C. So and also sending end voltage is equal to current passing through. Applying Kirchhoff's current law at the center node, sending end current is equal to capacitance current passing through capacitance plus IR current passing through receiving end. Okay. Now we have IC is equal to, we can substitute IC is equal to J omega Vc. Simply substituting this equation in this. So you will get IR plus J omega C into Vc. Now, so we have already seen sending end voltage is equal to Vc plus Is into Z by 2. So if we apply Kirchhoff's voltage law for the first mesh or first closed path, if we assume Vs is equal to Vc plus Is into Z by 2. So Vc already we have written. So substitute that. Is we have calculated in terms of IR plus J omega C into Vc. Okay. So if we substitute all the values instead of Is, instead of Vc, if we substitute, so you will get the entire equation like this. Vs is equal to sending end voltage is equal. Note down a little bit faster. Okay. నోట్ చేసుకున్నారా? ఓకే, సో ఇక్కడ దాకా ఏమైనా డౌట్లు ఉంటే చెప్పండి అమ్మా. ఎలాగా పోర్షన్ అవ్వదు. ఓకే, ఈజ్ ఇట్ క్లియర్? హలో, సరే, let us take 5 more minutes. Now the next step is to find out no load receiving end voltage. So in percentage regulation, while calculating percentage regulation, keeping the sending end voltage as constant. Okay, so no load receiving end, the voltage at the receiving end. So when there is no load means it is kept open circuited. Open circuited means current passing through this is zero. When current passing through this second part is zero, okay, this is zero. So there is no question of drop. The total entire voltage appears across this capacitance. So no load receiving end, that becomes VR dash. Okay, the same diagram I have represented in this fashion. So here the supply voltage, the same elements, but here this elements, because the load is open circuited, no load means current is zero. Whenever the current is zero, automatically So voltage drop is also zero. Current is equal to current is zero means voltage by impedance. Voltage becomes zero. So voltage is equal to zero. There is no voltage drop. Whatever may be the voltage appears at this point, the same voltage appears at this point. So VR dash, the same diagram I have represented in this fashion. When there is no load. Now, simply voltage division formula. Voltage at this point is equal to total applied voltage multiplied with that impedance divided by total impedance gives voltage across this. Okay, VR dash is equal to the total supply voltage Vs into so impedance. In this case, that is minus j by omega c. That is impedance across this whole divided by total impedance. Okay, that is voltage division rule. So using the voltage division rule, we have obtained VR dash. Once we obtain voltage at the receiving end, okay, now the regulation of for the T can be obtained as VR dash by minus VR by VR. Voltage at the receiving end is known value, that is given value. Voltage at the sending end, this is voltage under no load condition. So keeping sending end as constant, that's why we have obtained Vs first. The first step is finding Vs, voltage at the sending end, because the load voltage and load current, everything is known. Okay, known values. We don't know the sending end voltages and all. So that's why for the first step, we have to find out the sending end voltage, keeping the sending end voltage as constant, and find out the receiving end voltage under no load condition. That is second step. Okay. The first step is finding sending end voltage based on the receiving end voltage, okay, and receiving end current. The next step, finding the receiving end voltage under no load condition, keeping the sending end as constant, voltage as constant. Okay. Now, once we get those two, we can find out a regulation. Once we get the regulation, we can find out efficiency, power output. Output is, this is given, output power plus losses. We have already calculated the losses, current I square R. So this is 3 times if it is a 3-phase system, power 3-phase power output by 3-phase power output plus losses 3 times. In this case, the resistance R by 2, where in the first half, the current passing through first half is to IS. In the second half is IR. These two currents are different. Okay. So that's why IR square into R by 2. Then again IS square by into R by 2. So total multiplied with 3. The total 3-phase losses. Okay. You will get efficiency. Okay. So note on this. Let us end this session for today. So if you have doubts, you can bring it tomorrow. Now the time is already 10, almost 10. So thank you.